All right, the talk I call the Modern Daguerreotype in Science. It's about my research for the last 8 years on trying to investigate the nature of the daguerreotype, involving replication of various experiments with modern daguerreotypes, analyzing them with scientific equipment, and how it can support observation. This work began in 2007 when I spent a week at the George Eastman House. There was an invited group to investigate all of the known conservation treatments. We looked at diarrhea treatments, we looked at cyanide treatments, we looked at various electroplating, electrocleaning treatments. And after a week, we were addressing issues with the various methodologies. And the electrocleaning method that was used and at the time, and is used at the time, I found there was ways to address some of the problems that I was seeing with that methodology. So I worked for a while and I developed an improved version of electrocleaning. And I was quite successful. This is a daguerreotype that I cleaned. It's the Southworth Hawes daguerreotype. And I was interested in understanding if there was anything in the methodology that was affecting physical or chemical structure of the daguerreotype. So I applied for some funding to investigate the process. And we decided to look at the plates with wavelength dispersive X-ray fluorescence and scanning electron microscope. This is a wavelength dispersive X-ray fluorescence machine. It's quite large. It's the size of a 1956 Xerox copy machine. Those that are in the conservation field may be aware of the handheld WD-XRF machine. It's very common in conservation. Dushan Stulak at the Getty has used it frequently to analyze samples in situ. And that's the convenience and beauty of it. You can go to any object in any setting and you can analyze it and get a chemical signature back. The one disadvantage of the machine is that there are certain elements where you have an overlap. You have it's very incongruous. You can't quite isolate specific elements. The wavelength dispersive machine, on the other hand, is very, very effective at getting discrete elements. The disadvantage, of course, that you have to bring the samples to it, and they have to be 2 centimeters square to fit into the chamber. Now, I'm not really willing to cut up a Southworth Hawes daguerreotype into 2 centimeter square objects, but I have no problem cutting up my own work. So this is a quarter plate daguerreotype that I created with sample areas of highlight, midtone, and shadow, and each square with an identifying number. So I wanted to create a series of daguerreotypes going through the entire life cycle of the plate. So the first 3 plates are after fixation, in ungilded condition. I cut off the first row. Then I gilded the remainder of the plate. I cut off the next row, so then I have ungilded and gilded here. Then I tarnished the rest of the plate and cut off a row. And then with the remaining 2 rows, I thiourea cleaned 1 set of 3 and electrocleaned the other. And then we put it into the wavelength dispersive X-ray fluorescence machine. And we looked at every element on the periodic table. We could put the samples in and just set it on automatic and it would run. It could feed 32 samples at a time. One of the interesting things that we found, I'll just talk about sulfur here, is that the thiourea treatment did not remove all the sulfur. Electrocleaning was a little bit more effective in... Pause it here. Electrocleaning is a little bit more efficient in cleaning. Depending on the current density, electrocleaning is more efficient in removing silver. But what was really interesting and informative with this experiment was that the thiourea treatment actually removes gold on the plate. So in this sample you could see in the brand new plate and the tarnished plate and the electroclean plate, the gold content levels are the same. But with a 30-second immersion in thiourea, 60% of the gold is removed off the plate. And we have seen this with plates that have been treated with diarrhea, that is particularly ones that have been immersed for quite a while. You can see they look flat and lifeless, and the gilding is removed. Moving to the scanning electron microscope, here are images of the tarnished plate with the shadow, midtone, and highlight particles. What I found interesting about this is that the sulfur on the plate, the particles are very, very fine. They're not even a tenth of the size of even the smallest highlight particle. Yet, they obscure the image so effectively. The smallest particle, and it's blocking, it's absorbing the light, so you get the tarnish. I'm not the first to use a scanning electron microscope. This work was done by Alice Swan in the late 70s, Leon Jacobson, and probably the most well-known study using the scanning electron microscope is the work of Susan Barger and William White. And one of their observations from their finding, they looked at several daguerreotypes and they noticed this pattern on the substrate of the sample. And when they saw this, they wrote that they thought this to be etching of the surface due to cyanide cleaning. And of the almost 200 daguerreotypes examined in the Materials Research Laboratory, only 2% showed no sign of a previous cleaning treatment. Well, when I put my own samples into the scanning electron microscope, and I used as close of parameters with the machine as she was using, I noticed in my gilded daguerreotype, I saw the same pattern. Now, I did not clean this plate with cyanide. This is a brand new plate, and yet it shows a pattern. So it caused me to wonder, and when we looked at the ungilded plate, there was no pattern. Now the important thing to notice is the voltage used. The accelerating voltage used for the electron beam will determine how deep it penetrates into the sample. If you look at the work done by Barger and White, she's using 40 kilovolts accelerating voltage. That penetrates several microns deep into the surface. It's one reason why when she looked at the Cornelius plates, she was seeing copper. And so she thought that the quality of Cornelius plates was due to a copper-silver alloy, and that's not really the case. When I looked at Cornelius plates at Ryerson. When you reduce this accelerating voltage down to 5 kilovolts, you get much more careful surface information. And a Cornelius plate with lower voltage is 100% pure silver. Here we have a modern daguerreotype on the left and a 1850s daguerreotype on the right. And I'm just going to show you three different accelerating voltages. Here we have 7 kilovolts, and you do not see a pattern. As you increase the voltage, the pattern begins to appear. This is 11 kilovolts, and as we bring it up to 15 kilovolts, it gets even more noticeable. So at this point, I know that this pattern is not due to cyanide cleaning. It's absolutely due to the gold toning. I'm not exactly sure what it means, but it's from looking at my brand new samples and knowing how they're made, we're able to determine that this artifact, this visual thing we're seeing here, is absolutely due to the gilding. This was explained more clearly in the work by Patrick Ravinas in 2009, when he took a daguerreotype plate and using a focused ion beam was able to slice into the plate on edge. And once they did that, they could see that beneath the surface of the plate there were these voids, these gaps in the surface. And taking the work much further, Dr. Ed Vicenzi in 2011 continued to slice into the plate in 15 nanometer segments. And then putting the images together, you could actually move laterally through, almost like in a movie. You can see how the voids open up and how they close. You can see how the image particles form and form. So you can get a lot of information with that several layered sectioning of the plate. What's really interesting about this work was he was also able to do elemental mapping. And if you look at the images here, what you see is a image particle, which is a silver mercury amalgam. But more interestingly for me is that the gold toning not only encapsulates the plate, and it's a gold-silver amalgam. It's not pure gold. It's a gold-silver amalgam that not only covers the image particle, it also covers the plate surface and actually seeps under the particle to glue it down or cement it to the plate. And this is why when a plate is gold toned, it's much more difficult to remove the image particles through abrasion. This is why you can hand color a gilded daguerreotype, and you can't hand color an untoned daguerreotype. Moving back to 2005, we've seen these pictures of the George Eastman House. This was the Young America exhibition, 3 different venues from 2005 and 2006. This particular plate is from the Eastman House collection. The team at the Eastman House, this was a very important show. There was a lot of plates borrowed from institutions and private collectors. And in preparation for the show, they wanted to ensure that the plates were very carefully housed. There was a lot of research done. The plates were put into copper pans to scavenge any atmospheric pollutants. They were extremely well sealed. I joked that you could have exhibited these plates underwater. They were so well sealed. And yet, with careful photo documentation, it was noticed that within a month's time that this white disfiguring haze had occurred on the plate. It must have been absolutely devastating for the team to see this happen. So immediately the scientific community starts to try and solve and figure out what is going on with these plates. In 2008, Sylvia Centeno and her team, using surface-enhanced Raman spectroscopy, were able to look at several of the samples that were affected, and what she found was a chlorine peak, and actually the compound silver chloride. Well, everybody that has studied photochemistry, the mechanism of deterioration, they're believing that the silver chloride with exposure to UV light causes a breaking of the AgCl bond and redeposits silver on the plate. So that also has very severe implications. It's then thought these plates react to light, and because silver is being deposited on the plate, there's really no way that this can be treated. In 2011, she tried to replicate the mechanism by using my samples. I provided her with ungilded and gilded samples. She put them into a saline atmosphere for 3 weeks, and then into the scanning electron microscope, and she was able to find a very localized site of silver chloride. And what she also noticed when she used the electron beam to make the image, it also broke the bond and deposited silver. And so with that information, this then served for her as the proof that the energy is breaking the silver chloride and leaving silver on the plate. And then the scientists theorized with the silver chloride, and now with the revelation that there are voids between the surface, by 2013, this news hits the mainstream media. The Scientific American published an article in December 2012 titled "The Case of the Disappearing Daguerreotypes," and then the New York Times, the New Yorker, Portrait of Immortality Faded. And the verbiage in both articles is just about the same. It says, scientists theorize that the process draws silver to the surface to form subsurface voids, and in the case of the Southworth and Hawes, these voids may have trapped chlorine from Boston's salty air, and then the haze was due to light during exhibition. It's a good, plausible theory, but it doesn't explain these 8 plates. These 8 plates are from the George Eastman House collection. They haven't been exhibited in the 20th or 21st century. They lived their lives in storage in boxes. There is evidence, of course, that they were exhibited. If you look at most of the plates, they have perimeter tarnish on them. That tells me that in the Daguerrean era, when they're trying to show the best of their work to their clientele, they have the plates hanging on the walls on view. And this is where the perimeter tarnish in reaction with the brass mat has occurred. I cannot imagine they would have looked like this on their studio wall. I can tell you that they weren't actually, I've seen a couple of original plates, and their sealing method was not the best. They simply applied 2 pieces of tape, didn't even do a complete seal on the daguerreotypes. They actually offered a $5 discount to any customer that would bring back a plate that had ever changed. They thought that their process was so perfect and pristine that they were impermeable. In any case, once the Daguerrean era moves into the wet collodion era, they're no longer, Southworth has left the studio and Hawes is continuing on. He maintained the studio until 1901. He's now working with the wet plate process. A lot of these famous people, the plates were rephotographed in the wet collodion process to make prints. To do that, they would have had to have been unhoused, and then so they were never reglazed after that. So it's possible that many of these plates were then taken apart for rephotographing and then stored in plate boxes with no cover glasses. Here's an interesting pair. This is a stereo pair in the George Eastman House collection. The plate on the left has some sulfur tarnish, and it also has a little bit of haze along the right edge and a touch at the bottom. The plate on the right is in very good condition. Now, these were bought by Boyer in 1943 from the Holman shop, and they were gifted to the Eastman House in 1974. Now, there is some literature where Holman has cyanide cleaned a few plates, and he even talks about having had a disaster and a loss of image when he tried to cyanide clean. I don't imagine, I can't assume he cleaned the entire archive. I think it would have been cleaned on an as-needed basis for particular plates. Whether this plate is cleaned, we don't have the conservation history. The Eastman House doesn't have any records relating to this plate, so we don't know if any conservators at the Eastman House did any work to them. But there is one plate that seems to have more deterioration than the other. Where we can sort of tighten up our conservation records is if we look to the Feigenbaum sale. Now, this is a plate. The photograph was taken in 1998 by Chris Mahoney when he was documenting the plates in preparation for the auction. And this is his own photograph as he took it out of the box. And I want you to make note that there is tarnish on, not tarnish, this haze on this plate as it came out of the box. Now, it has not been exposed. There's no evidence that it's ever been on exhibition. There is no perimeter tarnish from that. It's probably one of the seconds, not chosen by a customer and just retained in storage without a cover glass. And when we look at, we look at the photograph in 1999, the official black and white version for the catalog, I want to call your attention to the hem of her dress where it meets the carpet. There, you can see the folds of the dress. But in the photograph taken in 2005 before the exhibition for the Young America catalog, you'll notice that the haze is much more obscuring. You can no longer see details at where the dress meets the carpet. Now, the owner of this plate is Michael Mannis, and he assures me that he did not exhibit this plate in his home. It was in his house from the time he bought it in a drawer in storage in relatively dry climate. So this advancement of the haze has happened in the dark. The Eastman House also took very careful annotated records describing plate conditions and describing the various bits of deterioration. This is the loan condition report. This plate was not rephotographed after exhibition. a few plates were observed to change significantly. The exact number I'm still unsure of. This was not one of them. It was not deemed that a second photograph was needed because the plate, based on the photographic annotated print, looked very similar. And Michael Mattis doesn't remember any alarms when the plate was returned from the exhibition. It came to my studio in 2013, and I photographed the plate, and it looks like the haze may have gotten worse from the period of 2005 to 2013. Although I will say that depending on how the plate is lit for photography, it may or may not look more prevalent. So without having the exact same lighting setup for every photograph, it becomes difficult to gauge. But it certainly seems to me that the haze has certainly gotten worse along the left edge and the right edge. Michael Mattis also bought this pair. And this became, when I saw this, I realized that this is a significant pair of photographs that may help lead us to understand the issue. This is a stereo pair made for the Grand Parlor Stereoscope. They were made the same day. They were shot within seconds of each other. They were sold together. They lived their entire life together under the exact same storage conditions through the studio, through to Feigenbaum, through to Sotheby's, through to Michael Mattis. These are twins that have never been separated since birth. Yet, one plate is in virtually pristine condition, while the next plate is significantly hazed. So I sent them to the Nora Kennedy and Sylvia Centeno, and they graciously agreed to analyze these plates at no cost. They were just as interested in seeing what we could learn from these plates as the owner and I was. And they had the plates, and they analyzed them with X-ray fluorescence and Raman, surface-enhanced Raman spectroscopy. But the report I got back from them was a little disappointing. What they said was, yes, we're finding chlorine on the plates, but we can't establish that it's any different between the haze area and the clean area. And so the haze may not be due to silver chloride. And they were also concerned about the appearance of the haze. In the main body of the haze, it looked like it was following some sort of aqueous tide line. And with that, the premise that they came up with was that this hazed plate must have been cleaned with thiourea. And so what is happening is a reoccurrence of tarnish due to thiourea. And to support that assumption, they looked at the back of the plate in a black stain, and they found mercury and gold in the stain. And knowing that thiourea can dissolve gold and mercury, this was part of how they had deduced that the plate was treated. The problem is that thiourea hasn't been used in 1943. It was invented in 1956. And the other problem I find is that I have found evidence of gold and mercury in stains on the back, which occurred due to the gilding process as the solution flows over the edge. In any case, it was an inconclusive report. I was very hopeful that we would find some clue to why one plate had changed so drastically and the other one was in virtually pristine condition. So my next step was to take the plates to Washington. And this is Dr. Ed Vicenzi. He's a colleague of mine, and he works for the Smithsonian Institution. He actually built the scanning electron microscope laboratory at the Museum of Natural History. He specified all of the software. He knows the equipment extremely well. And we built a special pan to receive the plates and attach them to the scanning electron microscope. And as far as I know, this is the first time ever that full plates have been put into a scanning electron microscope for imaging and analysis. We looked at the clean plate first, and we found really an absolutely beautiful gilded surface. There was no biological um, deterioration. There is no oxygen. There is no organics. The plate is absolutely pure Daguerrean, gold, silver, mercury. The microstructure of the gilding is very, very uniform. One of my own samples in a mid-tone, I was pleased to see that my microstructure and image particles were quite similar, although I can still tell at this level that my polish isn't quite up to the quality of the polish of Southworth and Hawes. Where it became very interesting was looking at the hazed plate. So in the apparently clean area of the hazed plate, the image looked very much like the other plate. But in the visibly hazed area, there was a significant pattern of irregularly shaped amorphous crystals, if you will. And when we analyzed those two areas, we found that in the visibly hazed area, 5 times higher chlorine levels than in the apparently clean area. There was still chlorine in the apparently clean area, but it was 5 times higher in the hazed area. And more significantly, in the other plate, there was 0 chlorine levels, which tells me this is not due to processing. This must be an environmental issue. The morphology of that silver chloride looked familiar to me. In 2010, I had put some samples of daguerreotypes that I had sensitized with iodine and bromine, but not fixed, imaged with or exposed to mercury. And placing them in the scanning electron microscope, I had a very similar morphology of halogens on the plate, which tells me that perhaps this chlorine has gotten onto the plate in a gaseous state. So I decided to do an experiment. I made a brand new daguerreotype. I cut it in half to have a pristine control sample. The other half I exposed to chlorine vapor. And that could be easily generated with swimming pool chemicals. I used 2 grams of calcium hypochlorite and put the plate into a, you might say, sensitizing box, and let chlorine vapor react with the plate for 20 minutes. I also made sure to dry the plate in the 19th century method. I've always suspected that even though a perfectly dried plate, you may see no visible tide lines on the plate, there is still a signature on the plate where the water recedes. And I dried this plate with a pair of pliers and an alcohol lamp, and you could see that the chlorine on the plate has not evenly reacted with the plate. There are areas where it seems to have more chlorine on it than the other. So I photographed it immediately coming out of the chlorine vapor, and then I put it away in dark storage. 2 days later, I took it out of the dark storage, and I was astonished to see that it had significantly hazed. And 2 more days after that, the haze had gotten worse. And 10 days, it had gotten even worse. And this is happening in dark storage. I took them to Ryerson to the scanning electron microscope and analyzed the haziest and least haziest area and the clean area. And the spectral mapping is virtually identical to the mapping on the Southworth Hawes plate with the elevated chlorine levels. Now, what is causing the hazing? It occurred in the dark, but I had to take it up to photograph it. So I was wondering, is the light causing the haze to form just because I took it out to photograph? But plates that were coming out of the boxes in 1998 with haze on them. So in the dark, this haze was occurring. So I wanted to do a more refined experiment. I made a new plate. I exposed half of it to chlorine vapor, and under safe light, I exposed it under safe light to chlorine vapor, and then I masked half the plate 90 degrees to the chlorine to block all light. And then I put it in my north light window, and using a spectrophotometer I measured the intensity of the light, and this plate got the equivalent of 50 times more illumination than the lighting for the Young America exhibition. The average lux for the day was 4,860. So significant amount of light. After that, I took the plate and I FedExed it down to Ed Vicenzi in Washington, and under safe light he had put it into his own scanning electron microscope, and here are the images that resulted. The clean plate with no chlorination looks like a brand new daguerreotype. The plate that has no exposure to light, again we have these amorphous crystals of silver chloride, very tiny particles and very frequent particles. But if you notice the plate where it was exposed to light, the particles have gotten bigger and fewer. And when you look at the chlorine signals, the chlorine levels are virtually the same, whether it's exposed to light or whether it's not. There's maybe very slight loss of chlorine on the light exposed. So going back to the mechanism of what we're seeing here, it's been proposed that the light is causing the silver chloride to redeposit silver on the plate. If that were the case, the chlorine would leave the plate. That's called photolytic. That's where the energy causes a breaking of the silver chloride bond. So the chlorine leaves and the silver gets deposited on the plate. But I must remind you that that theory is based on salted paper printing, which requires an excess of silver nitrate to sustain a printout reaction. I've shown you the particles are very, very small particles appear black. When you print out silver, you get a black particle. This is a white particle. This is a large, scattering, hazy particle. And another possibility is that light energy can be absorbed by the compound to excite the electrons in the chemical bond, raising their energy level. So causing a coarsening. So what I think the mechanism here is basically Ostwald ripening, and it's natural for very small particles with large surface area to want to join together to form larger particles with a smaller surface area. Emulsion technologists use this when they create halogens to increase their film speed. By allowing the gelatin to be liquid longer, you allow for more ripening to occur before you set the gelatin, so you create a larger silver chloride, silver bromide, silver iodide halogen and get a faster working film. If we think of the ripening, it also explains what I've observed as a daguerreotypist. When I sensitize a plate, that it gains photographic speed if I wait. So what I believe here is not a deposit of silver causing the haze, a redeposited silver, but rather the silver chloride halogen on the plate is ripening into a larger, more visible crystal. Which explains the ripening is going to happen. It wants to happen whether it's in the dark or whether it's in the light. Which explains why they come out of the box in a hazed condition. But it can also explain why the haze can be promoted by light energy. It just quickens up the Ostwald ripening reaction. But where does the chlorine come from? I propose it's most likely the storage. In the Eastman House archive, in the Eisenberg archive, in the Feigenbaum archive, the plates were sold from Holman in the boxes that they were stored in the studio. These are the Southworth and Hawes plate boxes from the Eisenberg collection. The Feigenbaum sale, there was 68 full plates in, there were 22 in tin box A, 24 in tin box B, and 22 in wood box 6. Also in the Eisenberg collection is a stack of brand new plates that have never been used, never been polished. They're knife plates. And when I pulled them out of the box, I noticed on the left and right edge a deterioration. And when we placed this plate into the scanning electron microscope, we got a huge chlorine peak. Now the edges of these plates were what were in contact with the wood of the wooden boxes. The other thing I noticed was that the first plate in the box was the most heavily tarnished, and each plate further down the row had less and less deterioration. So going back to the theory of putting the Southworth and Hawes plates in copper pans to scavenge atmospheric pollutants, the first plate in the box served the same role. And it's a possible explanation for why just a few of the plates had the most haze. Perhaps their position in the box had an effect on how much chlorine it received either from the box or from the atmosphere. So the next question obviously is silver chloride soluble? Is there a way to fix this problem? Well, literally, yes. Dip the plate in film fixer, the silver chloride comes right off. Now, sodium thiosulfate has sulfur in it. I didn't want to try any conservation treatment that would introduce more sulfur into the problem. So there are other solvents for silver chloride, and so this is the woman in damask evening gown. Notice also that the white haze is predominantly at the bottom and on the left and right edge, and none at the top. If you think about the plate box, those three edges are what are in contact with the wooden box. The lid is spaced away from the top. And so this plate is also hand colored. The client wanted it treated, but I did not want to lose the coloring. I did not want to immerse the plate. So I developed a system, practicing on my own plates, to see what would be effective, and with a local treatment of ammonia solution, was able to dissolve the silver chloride. So this is the plate pre and post treatment. The ammonia will not remove sulfur. I had no intention to remove the sulfur on the plate. I wanted to remove the disfiguring white haze. And here's the right half of the stereo pair. The haze is very severe, and again, following what I believe to be invisible evidence of the original drawing of the plate when it was made. And here it is, before and after. So in conclusion, the white haze, in this case, is due to silver chloride compounds. Silver chloride may form visible haze even in dark storage. The mechanism of deterioration is not necessarily redeposited silver. I won't rule it out, but it's not necessarily redeposited silver. More likely, possibly Ostwald ripening. The problem is due to storage and environment. It's not inherent in every daguerreotype. And conservation treatment can remove the haze. And I'd like to acknowledge the owner of the plates, Michael Mattis, who was very patient. I had the plates for over 2 years while we were investigating the problem. I'd like to thank Dr. Ed Vicenzi, who volunteered to work no charge at with the scanning electron microscope. We were there for 2 weeks. Zhang Li, Ryerson University, as well, with his work on the plates. My colleagues at AMC Toronto. I'd like to thank Christopher Mahoney for his careful notes on the Feigenbaum sale and original photographs. Brett Romer for his reminiscences of conservation histories at the George Eastman House and the Feigenbaum sale. Irving Poborowski for reminding me that silver chloride is soluble in ammonium hydroxide. And thank Sylvia and Nora for their assistance with analyzing the plates at the Met, and Ralph Wiegand for his access to the conservation reports for the Young America exhibition. All right.